Today's lesson is on continuity of flow. Continuity of flow is a continuation of our study of dynamic fluids. Dynamic fluids, again, are fluids that are in motion. When we're talking about moving fluids, one of the first things we need to know is flow rate. You guys already know that flow rate tells you how much fluid in terms of volume is flowing per second. We know that it's measured in cubic meters per second, and we know that cubic meters are large. So expect to get small numbers for flow rates. How do you predict the flow rate? Well, it turns out to be the product of the area of the faucet times the velocity of the water coming out of the faucet. Okay? So the velocity and the area multiplied together get your flow rate. And that would allow us to figure out how much time it takes to fill a container, or it would let us know how much volume we can get in a given amount of time. So today we want to expand upon that by learning about continuity of flow. And continuity of flow applies when you have pipes of different sizes that are connected through a coupler. You have water flowing through the one pipe, and we'll say it has a cross-sectional area of A1, and it has a speed of velocity 1. It goes through the coupler and emerges into a smaller area with a different velocity. What do you think is going to happen with that velocity? Is that going to be moving faster than it was in the first pipe? Slower than it was in the first pipe, or at the same speed as the first pipe? Well, if you've ever covered the end of a hose with your thumb to give a smaller exit area, you know the answer to this. You know that as the area gets smaller, the velocity gets larger. When we contract our system, it makes the water speed up. What's going on here is the idea of continuity of flow, which says the flow rate must be equal in both parts of that pipe. Why is that? Well, so long as there are no leaks from the system. If there's leaks, then all bets are off. But if there's no leaks, whatever water entered into the coupler must leave from the other side. So if 20 milliliters go in, 20 milliliters must come out. Matter cannot just disappear. All right? Flow rate equals flow rate. It's called continuity of flow. And if you look at this, you can see the particles moving slow. Now the particles are moving fast. The reason is there's less area, so the only way to maintain that flow rate is for them to have sped up. Continuity of flow. How do you solve problems with continuity of flow? How can you predict how fast the water will be moving after it enters into the smaller pipe? Well, you find the flow rate on your first part. So you get area 1. You then take area 1 multiplied by velocity 1 and get flow rate 1. Whatever that flow rate is, you set it equal to flow rate 2. Then you find the area of the second section. And you can solve for the velocity of the second section. You should find that if the area gets smaller, the velocity gets faster. This does not just apply to water, it applies to any fluid, including things like air. So you'll notice this leaf blower advertises itself at a powerful 230 mile per hour speed for the air coming out. You'll also notice maybe a little asterisk, which means there's something they're not telling you about that 230 miles per hour. If we look at the data, again, it tells us we have an airspeed, a maximum airspeed of about 230, but once again we get our asterisk. Again, something is going on here. When we flip the box over in very small print, we see that the asterisk means we can only get this speed by means of using a concentrator. So what we want to do is figure out how small we're going to have to make the pipe to get this speed. So you can see how the pipe narrows naturally as it goes toward the end where the air comes out. Since it's getting narrower, the air is going to be getting faster, but not 230 miles per hour. You cannot get that from the factory. You need to buy a special concentrator. So let's figure out what that concentrator would need to look like. We start by realizing that they tell us the flow rate right on the box. We know that flow rate equals area times velocity. Take this flow rate, change it from cubic meters per minute to cubic meters per second. So if you can't read that, it says 10 meters cubed per minute. And again, you need to convert it. For the velocity, you want to use 230 miles an hour, but you want to convert it to meters per second. We now have everything we need to figure out the area of that magic concentrator that they don't even give you when you buy the leaf blower. Okay, so once you got the area, plug in, solve for radius, and see just how small of an opening is required to create these tremendous hurricane force speeds. In fact, these are faster than a hurricane. Hurricanes usually only get up to about 100 and some miles an hour. This is almost tornado speeds, okay? Cannot happen without the use of a concentrator, and you're trying to figure out how small that concentrator has to be. Anyway, with that in mind, I'm going to ask you guys to finish up those problems, the one with the air, the one with the water, and hopefully you understand this idea of continuity of flow.